Hello, how is everyone over there? I want to share something on a topic that I was to discuss with you today in the evening, and because of unavoidable circumstances I can't be able to come in for the lesson, and I really want to be able to share something so that I can be able to share via WhatsApp. I can go through what I've shared, then be able to ask questions maybe tomorrow later in the day when we shall be able to meet for our one-on-one lesson. We want to discuss something on chlorine and its compounds, and what I just want to actually introduce first is that chlorine is one of the elements found in the periodic table. It's among the first 20 elements. Something funny about this element is that it's actually a metal. It is found in group 7 and its electron configuration is 17. Being in group 7 means that it has 7 electrons in the outermost energy level. When its electron configuration or arrangement is written, it clearly has 2 to 8 to 7. The first energy level must have a maximum of 2 electrons. The second energy level must have a maximum of 8 electrons. When you add the electrons filled in the first 2 energy levels, leaves the third energy level with only 7 electrons. That leaves chlorine getting to that point of actually belonging to group 7. This element is found in period 3. What does this mean? It actually ends up getting found in period 3 because it has a maximum of 3 energy levels, 2 to 8 to 7. So 2 to 8 to 7 means that it ends up having only 3 energy levels. That makes it to be actually a member of period 3. Why do I say that chlorine is a non-metal? If you clearly actually tailor down this content to be able to have a better understanding of all this information, you'll realize that all those elements that react by gaining are non-metals. And if I have a clear indication of this, I can have 1, 2, 3, 4, 5, 6, 7. Now, if an element has either 1 electron, 2 electrons or 3 electrons in the outermost energy level, then that means that that element is a metal. I'll repeat this. If an element has 1 electron, 2 electrons or 3 electrons in the outermost energy level, then that means that element is a metal. If an element has 5, 6, 7 as electrons in the outermost energy level, then that means that element is a non-metal. So having 1, 2, 3 in the outermost energy level means that this element can only be able to lose. And remember, either the second energy level or the third energy level has only to be able to have 8 electrons. So if this element has 1, 2, 3, then that means that it is very easy for it to either lose that 1 electron, to either lose that 2 electrons, or to lose the 3 electrons, but very hard for it to gain 7 if it has 1, to gain 6 if it has 2, or to gain 5 if it has 3. That actually makes the element to be a metal. So all metals react by losing, and all non-metals react by gaining. Chlorine has an electron configuration or an electron arrangement of 2 to 8 to 7. So that means that if it has 7 electrons in the outermost energy level, it is very easy for it to gain 1 electron than to lose 7 electrons. That is easier. It can clearly be able to get understood by any student. Now moving downwards, chlorine does not exist just freely in the atmosphere. Something fun with it is that it will always be found in combined forms. That means, for example, it is found bonded strongly with this other metal called sodium, and whatever they form is called sodium chloride. So sodium chloride is also referred to as rock salt. So that clearly tells you that sodium and chlorine can combine and be able to form a strong bond, an electrovalent bond or an ionic bond, and in that case this makes chlorine not to actually be able to exist alone in the atmosphere. So it is actually found in combined forms where it is clearly able to combine with other elements to form compounds. When chlorine exists just as an element in the atmosphere, it won't be found as Cl, capital C small l, as its chemical formula. It is found to actually exist as a gas. It is an example of what we call a diatomic gas. That means di means two, so that means we have two chlorine atoms combining to give you Cl2. That is actually chlorine gas made up of two atoms, diatomic gas. Other diatomic gases are like oxygen, hydrogen, nitrogen gas. They are called diatomic because they are actually made up of two atoms. To be able to understand this one in a better way, you'll realize that chlorine can be able to get prepared in the laboratory, and for this gas to get prepared in the laboratory, we shall always be able to use what we call strong oxidizing agents. Some of these strong oxidizing agents that we can be able to use are like, we have potassium manganate 7, which is purple. Potassium manganate 7, which is purple on getting dissolved in water. We have also other oxidizing agents like lead 4 oxide. Other oxidizing agents are like manganese 4 oxide. For example, if I may want to begin with potassium manganate 7, you'll realize that, don't be surprised, I'm sometimes even looking at something on top of my table. I'm trying to actually come up with those equations and be able to explain to you in a better way. So if I have potassium manganate 7 in a layman's language is referred to as KimNO4. Potassium manganate 7 can get reacted with hydrochloric acid to give you potassium chloride and chlorine gas, manganese 4 chloride and water. Potassium manganate 7 is getting reacted with hydrochloric acid to give you potassium chloride, chlorine gas, manganese 4 chloride and water. To balance this chemical equation, my teacher gave me a shorter way of actually arriving at the final answer in terms of balancing the chemical equation, which is this shorter way of doing it. You can just be able to put 16 on hydrochloric acid, put 16 on hydrochloric acid, and then put 8 on water. Why do I put 8 on water? Because when you put 16 on hydrochloric acid, you'll end up having 16 hydrogen atoms. Then to balance the chemical equation on both the reactant side and the product side, you have to put 8 on water, so that when you take 8 times 2, you get 16 hydrogen atoms. Now, on your product side, you have 8 oxygen atoms. To balance the chemical equation in terms of the number of oxygen atoms, you have to put 2 on potassium manganate 7, previously known as potassium permanganate. So if you put 2 on potassium permanganate or potassium manganate 7, you'll end up having 8 oxygen atoms on your reactant side and 8 oxygen atoms on your product side. Why do I have 8 on my reactant side? That is 2 times 4. Now, to finish this chemical equation, you can put 2 on potassium chloride. Why do I put 2 on potassium chloride? Because on my reactant side, I have 2 on potassium manganate 7. That leaves potassium with 2 atoms. On my product side, I have to put 2 on potassium chloride to also have 2 atoms of potassium on my product side to balance the chemical equation as well. Now, to proceed forward, I'll put 2 on manganese 4 chloride. Why do I put 2 on manganese 4 chloride? Because I have put 2 on potassium manganate 7, and that leaves manganese ions to have actually 2 as the number. So to balance it on actually other side, you can be able to put 2 on manganese 4 chloride, so that you can have 2 Mn on your reactant side and 2 Mn on your product side. Then to finish this, you should ask yourself, how many chlorine atoms do I have on my reactant side? They are 16, because you had placed 16 on hydrochloric acid. Now you have 2 chlorine on KCl, you have 4 chlorine on MnCl2, that gives you 6. Now how many are remaining to give you a total of 16? You'll take 16, the total number on your reactant side, minus 6 on your product side, the 2 on KCl and the 4 on MnCl2, to end up remaining with how many? 10. Now how do I balance the equation? I'll put 5 on Cl2 to end up having Cl2 having 5 behind it, so that when I take 2 times 5 I get 10. So 10 plus 2 plus 4, I get 16. The equation is well balanced. So potassium manganate 7 plus hydrochloric acid to give me potassium chloride plus chlorine gas plus manganese 4 chloride plus water. 2 on potassium manganate 7, 16 on HCl, 2 on KCl, 5 on Cl2, 2 on MnCl2, and 8 on H2O. Now using other methods of actually collecting this gas as well in the laboratory, when it's well prepared, you can as well have manganese 4 oxide getting reacted with the same acid, hydrochloric acid, to give you MnCl2 plus Cl2 plus water, MnCl2 plus Cl2 plus water, MnCl2 plus Cl2 plus water. I can put 2 on water, I can put 4 on HCl, that gives me 4 hydrogen atoms, 4 hydrogen atoms. I have 4 chlorine atoms, 4 chlorine atoms, 2 oxygen atoms, 2 oxygen atoms. That equation is well balanced. MnO2 plus 4ClH to give us MnCl2 plus Cl2 plus 2H2O. That is great. Now to actually have also this gas getting collected, I can as well use lead 4 oxide. What's the chemical formula of lead 4 oxide? PbO2. PbO2, lead 4 oxide. Chemistry is funny. If someone says lead 4 oxide, don't write 4. You actually divide that number by 2. So what do I get? PbO2 and not PbO4. So I have PbO2 plus HCl to give me PbCl2 plus water plus Cl. Now how do I balance this? I can put 2 on water, then I put 4 on HCl, and the chemical equation for sure gets balanced. Yeah, that's true. So PbO2 plus 4HCl to give us PbCl2 plus 2H2O plus Cl2. That is great. That is actually very great. So in all of these equations, we are arriving at actually collecting a gas called chlorine gas. In as far as chemical equations are concerned, we have 4 main principles that hold in as far as getting any mark in relation to this area is concerned. So number 1, you have to use the right chemical formula for each and every element. Number 2, you must ensure that the right products are written. No exaggeration, no any form of guesswork. You have to actually ensure that whatever you are writing on your product side are the right products that are supposed to be obtained when a chemical reaction takes place, in such a way that when 2 reactants come together, whatever you have written actually depicts the truth in as far as whatever has taken place is concerned. Number 3, you ensure that you write the right state symbols. We have 4 main types of state symbols. You have what you call the liquid state, the gaseous state, the solid state, and the aqueous state. Of course, you can give examples like metals. They are all solids. When metals react with oxygen, they give you what you call metal oxides. All of them are solids. I'm just giving examples of solids. Number 2, the liquid state. We have several types of liquids. Anyone can know what a liquid is. We have what you call aqueous. Aqueous means a solution. There must be a solid and a liquid. All acids, of course, are aqueous unless more water has been added. That makes that to be a liquid and not an aqueous solution. The last part is actually what we call the gaseous state. Everybody knows gases, unless otherwise. For example, in some cases where you'll find the water getting heated to that level of turning into what we call steam or vapor. Then that one does not become a liquid again, it becomes what we call what? Steam. Very good. To move forward, we shall look at what we call the physical properties. The physical properties. I've just been able to write some of these chemical equations here. You can be able to see. You'll realize that I had begun by taking potassium manganate 7. I don't know if you can be able to see it very well. Potassium manganate 7. It's very unfortunate it can't be seen very well. Potassium manganate 7 react with hydrochloric acid to give you potassium chloride plus chlorine gas plus water plus manganese for chloride. So, what are the physical properties of chlorine? Number one, chlorine is a greenish yellow gas. Apart from chlorine gas, you realize that the other gas that does actually have what we call a colored aspect in terms of its identity is the gas we call nitrogen 4 oxide. Nitrogen 4 oxide is reddish brown. Chlorine gas is greenish yellow. Up to what we call the O level, you'll realize that those are only the two main gases that are actually colored. Others are colorless, like hydrogen, oxygen, chlorine, which is actually the greenish yellow gas. I don't actually knocks it out. We have what we call the nitrogen gas itself, the nitrogen 1 oxide, the nitrogen 2 oxide, the sulfur 4 oxide. They are actually colorless gases. Students, you should note that apart from chlorine being greenish yellow, it is actually an acidic gas. This gas has an effect on moist blue litmus paper. It turns moist blue litmus paper red. This gas is denser than air. It being denser than air allows it to get collected by what you call downward delivery or upward displacement of air. This gas, at the same time, is a gas that is actually more soluble in water. It can't get collected over water. It is very soluble in water. That makes it possible for it to get collected by a method called downward delivery or upward displacement of air. Chlorine gas does not support combustion. It will actually be able to actually have a burning splint getting blown out. It doesn't support combustion. It doesn't relight a glowing splint. It doesn't make a burning splint to burn more. So it doesn't support combustion. Those are just some of the physical properties of chlorine gas. And a student who actually finds himself or herself doing the O level in whichever country he or she may be should be able to have at least 2 or 3 of these physical properties, because they normally get tested in the examination. Now, chemical properties. The first chemical property is where chlorine gets dissolved in water. When chlorine gets dissolved in water, chlorine forms what we call chlorine water. Chlorine, Cl2, capital C small l subscript 2. When chlorine gets dissolved in water, Cl2 plus water, it gives you what we call chlorine water. What is actually the composition of chlorine water? We have what we call HOCl, that is what we call hypochlorous acid or chloric 1 acid, and HCl, hydrochloric acid. These two compounds are the ones that form what we call chlorine water. The compounds that result when chlorine gets dissolved in water. This chlorine water is pale yellow. This HOCl will act as a bleaching agent. Chlorine bleaches by what we call oxidation. It bleaches by adding oxygen on the substance is actually bleaching. It bleaches by adding oxygen on the substance it is bleaching. It actually bleaches by what we call oxidation. Its bleaching action becomes very permanent because it bleaches by oxidation, by adding oxygen on the substance getting bleached. Let me give you an example. If I have chlorine water, now specifically I may tailor down this discussion to HOCl. HOCl plus a dye, a colored substance. What happens? The dye picks the oxygen. The HOCl adds the oxygen to the dye. On getting that oxygen, the dye becomes colorless. So what has happened? The dye has been bleached. once it takes the oxygen from the HOCl. Students, that only oxygen, that lone oxygen that gets added to the dye is called nascent oxygen. That only oxygen that gets added on whatever is getting bleached is called nascent oxygen. Nascent, N-A-S-C-E-N-T, nascent oxygen. Nascent oxygen. That is actually what happens when chlorine water gets exposed to sunlight. The sunlight breaks down the HOCl to HCl and O. The sunlight breaks down the HOCl, the chlorine water, to HCl and O. That oxygen is called nascent oxygen. That is actually what makes the chlorine water to change its color. So the sunlight can break down the HOCl to HCl and O. The HCl now is now the hydrochloric acid. The O is the one we are referring to as the nascent oxygen. Moving forward, you'll also realize that chlorine can be able to combine with the metals. For example, it is a highly reactive nonmetal. It is actually able to occupy the second position as far as the group 7 elements are concerned. The first element in that group is called fluorine. The second one below it is called chlorine. Chlorine is the most reactive nonmetal. So it can easily be able to combine with the metals to form what you call metal chlorides. To give an example, iron can react with chlorine to give you what? Iron 3 chloride. Remember this, students, if you have been given a chance of writing a chemical equation when chlorine reacts with iron, don't write the product as iron 2 chloride. Just in case you get a question where chlorine reacts with a metal that has more than one oxidation state, we always write the product with that higher oxidation state and not that lower oxidation state. Why? Because the higher the reactive and nonmetal is, the product we get should have an oxidation state higher in as far as that metal is concerned. So don't write iron 2 chloride, you will write iron 3 chloride. There is also a possibility of getting iron 2 chloride, but due to the reactive nature of chlorine, we do not get iron 2 chloride. We get what we call iron 3 chloride, which is actually a black solid. So chlorine plus iron 3 chloride, black crystals. Magnesium can as well react with chlorine to give you magnesium 2 chloride, which is a white solid. Sodium can as well react with chlorine to give you what? Sodium chloride, which is a white solid. Actually, it is very, very important for me to actually take note of this. Please ensure that when you are reacting chlorine with metals, whether in the laboratory or anywhere else, don't ever try this. Group 1 elements, those are sodium, potassium, francium, caesium, and rubidium, should never be able to get used in as far as any of these reactions are concerned. They are highly reactive. They react explosively. They react violently. They can present an explosion in an environment. Who wants to die as early as this? No one. So never ever make a mistake of trying this out, because it's very, very dangerous. We only use the group 2 elements like magnesium, calcium, strontium, barium, and radium, but not group 1 elements. It is very, very dangerous. Very, very dangerous. Now to move forward, chlorine can as well react with oxygen, but the rate at which it reacts with oxygen is very, very slow. To speed up the reaction, we have to actually embrace a source of heat. We need to actually speed up the reaction by actually increasing the temperature. For example, chlorine can react with oxygen to give you what you call dichlorine heptoxide. Dichlorine heptoxide, that is Cl2 plus oxygen. That gives you Cl2O7. Dichlorine heptoxide. Di means 2, so dichlorine. Then heptagon, dichlorine heptoxide. That means that now you have what you call an oxide of chlorine, dichlorine heptoxide. Again, chlorine can react with oxygen to give you what you call what? Dichlorine oxide, Cl2O, dichlorine oxide, dichlorine oxide, dichlorine oxide, dichlorine oxide. Another chemical property in as far as chlorine is concerned, you will realize that chlorine sometimes, and mark my words, sometimes can become a very strong oxidizing agent. How does it actually show its oxidative property? For example, you will realize that chlorine can be able to oxidize sodium sulfite, Na2SO3. Chlorine can oxidize sodium sulfite, so that at the end of the day, you'll end up having what you call sodium sulfate plus chlorine, sodium sulfate. A strong oxidizing agent. To balance the chemical equation, you'll write Na2SO3 plus Cl2 plus H2O. Why is the water getting used here? The water must be able to actually form a solution of sodium sulfite. Remember, sodium sulfite will dissolve in water. Why? All sodium salts in the whole world are soluble in water. So that gives you sodium sulfate plus hydrochloric acid. So sodium sulfite has been oxidized to sodium sulfate. Sodium sulfite has been oxidized to sodium sulfate plus hydrochloric acid. That's great. Now, to finish my discussion for today, and if in case you may have a question, please be ready to respond to this by actually asking any question tomorrow. We shall be meeting. You'll also be able to realize that chlorine has some applications in the environment. It can get used in different areas. For example, to just look at some of the uses where chlorine can be used, you'll realize that chlorine is used to form what you call chloroform. To manufacture chloroform. Chloroform is used as an anesthetic. To relieve pain, just in case you may want to have what you call surgery. You see, chlorine is used to form chloroform. Chlorine is used to manufacture chloroform, which is used as an anesthetic to relieve patients from pain when they are undergoing surgery. Yes, very good. Number 2, chlorine is used to manufacture some compounds such as CFC. What is CFC? Chlorofluorocarbons. You see, chlorine is used to manufacture chlorofluorocarbons. Now, chlorine has also been able to get used in manufacturing hydrochloric acid. I'll just be able to give you some of the uses of CFCs or chlorofluorocarbons. Chlorine has also been used to actually manufacture hydrochloric acid. If you look at hydrochloric acid, it's actually HCl. It has chlorine. So chlorine must be used in the manufacture of hydrochloric acid. Chlorine also has been actually able to get used in what you call water treatment. You have heard of this issue called the chlorine water. It's actually added to water to kill germs. So chlorine is used in the treatment of water. Again, chlorine is used in what you call sewage treatment. It is actually added to sewage to kill all the microorganisms, isn't it? So sewage treatment and water treatment. Chlorine is used to manufacture what you call polyvinyl chloride, which is used to manufacture plastic pipes. That is actually an example of a polymer. You'll go and discuss what you call organic chemistry too in form. You'll realize that you'll be able to actually discuss PVC as one of the polymers. Polyvinyl chloride is a polymer used to manufacture plastic pipes. That is very, very important. Now, something else to note is that chlorine is also used to manufacture some insecticides, germicides, and fungicides. Why is it very appropriate in manufacturing insecticides, germicides, and fungicides? Because of its poisonous nature. It has a choking smell, an irritating smell, a pungent smell that can cause suffocation. So you don't even want to be in a room where this gas is actually able to get to your nose. You'll die. So its ability to cause any form of poisoning makes it to become a very good material in manufacturing insecticides and germicides. You see, in fact, it has been able to get used in manufacturing some of these insecticides that are very, very harmful to the environment. These insecticides or germicides or fungicides have even been able to get prohibited by some countries. There was a meeting held in United States of America. It was called the New Convention Stockholm's meeting that prohibited the use of chlorine in manufacturing some of these insecticides and germicides and fungicides. Why? Because the harm they are doing to the environment is more than the benefits they have to us as individuals. Manufacture fungicides, germicides, and pesticides. That is very, very important. Very, very important. Now, what are some of the uses of the CFCs or the chlorofluorocarbons? Number one, CFCs are used as refrigerants. CFCs are used as refrigerants. They are examples of gases used as what? Refrigerants. To preserve perishable what? Goods in domestic what? Regions, especially at home. So, manufacture of refrigerants. CFCs are used to manufacture aerosol propellants. Propellants. CFCs are used to manufacture aerosol propellants. Some CFCs are used as insecticides and as well fungicides. Insecticides as well as what? Fungicides. How is hydrochloric acid manufactured? Hydrochloric acid is manufactured when a smaller amount of hydrogen gas is burned excessively in chlorine gas. A small amount of hydrogen gas is burned excessively in chlorine gas. Why do we use a small amount of hydrogen gas? To prevent an explosion. Hydrogen gas can easily explode. Explode when it actually gets introduced to another gas in the presence of heat. So what am I saying here? A small amount of hydrogen gas is allowed to burn in excess chlorine to give you what? Hydrogen chloride gas. The hydrogen chloride gas is allowed to actually ascend upwards into another chamber where we have what you call glass beads. The glass beads offer a larger surface area to dissolve the gas in water. There is a downward flow of cold water. That downward flow of cold water actually meets the hydrogen chloride gas in that region where we have what you call the glass beads. The glass beads offer a larger surface area for dissolving the gas. So the gas dissolves in the water to form what you call hydrochloric acid. The hydrochloric acid gets stored in steel tanks lined with rubber. I think you understand the meaning of all this. Why? Because these acids are very corrosive. They can attack metallic structures. So the acid gets stored in metallic tanks or steel tanks lined with rubber to prevent the acid from attacking what? The metallic lining of that tank. What are some of the physical properties of chlorine gas and even hydrogen chloride gas? Some of these physical properties of chlorine gas and hydrogen chloride gas are similar. If you look at the physical properties of hydrogen chloride gas, you realize that this gas is also colorless. It is very soluble in water. It has also an irritating or choking smell. This gas as well is denser than air. It gets collected by downward delivery or upward displacement of air. It is actually not collected over water because it's highly soluble in what? In water. This gas has an effect on moist blue litmus paper. What does it do? When the litmus paper is moist and that gas gets in contact with that litmus paper, the gas dissolved in the moisture or the litmus paper to form hydrochloric acid. The hydrochloric acid provides an acidic environment. That acidic environment will change the moist blue litmus paper to red. That means hydrogen chloride gas is an acidic gas. It has the ability to turn moist blue litmus paper to red. What are the chemical properties of this hydrogen chloride gas? When this gas gets dissolved in water, it actually portrays its acidic properties. On portraying its acidic properties, number one, it can react with the metals to give you metal chloride and hydrogen gas. This metal chloride or these metal chlorides are actually salts, and hydrogen gas is also given out in form of what you call effervescence, or gas bubbles are getting produced when the reaction is actually taking place. So for example, when I take magnesium plus hydrochloric acid, I will get magnesium chloride and hydrogen gas. There is effervescence due to this gas which is also getting produced. Moving forward, hydrochloric acid can as well react with metal oxides. I can give this example. If I have copper 2 oxide, and remember, when metals react with oxygen, they give you metal oxides. Metal oxides are basic. Then non-metal oxides are acidic. Copper is a metal. When it reacts with oxygen, it gives you copper 2 oxide. That is a basic oxide. Sulfur is a non-metal. When it reacts with oxygen, it gives you sulfur 4 oxide. Sulfur 4 oxide is acidic. It dissolves in water to give you what you call an acidic solution. So hydrochloric acid is an acid. Then metal oxides are bases. When an acid reacts with a base, the products are salt and water. So copper 2 oxide plus hydrochloric acid. Copper 2 oxide is acting as a base. Hydrochloric acid is acting as what? An acid. When they react, they give you copper 2 chloride, which is now the salt plus water. Copper 2 chloride, the salt plus water. When hydrochloric acid reacts with bases with OH, there are 3 examples of bases in chemistry. Number 1, metal oxides are bases. Number 2, metal carbonates and metal hydrogen carbonates are bases. Number 3, metal hydroxides are bases. So I've given you an example of where we have a metal oxide reacting with an acid to give you salt and water. And as well, which other compound can we use for us to get the same products? Which other base can we use for us to get the same products? We can as well have sodium hydroxide, OH, metal hydroxide, also a base, reacting with hydrochloric acid to give you what? Sodium chloride plus water. So don't get surprised, oh, you know what, blah, blah, blah. Just know from today that examples of bases are metal oxides, metal hydroxides, metal carbonates, and metal hydrogen carbonates. When they react with acids, water must be one of the products. What is the name referring to this type of reaction? The name that is actually used to refer to this type of reaction is called neutralization. Neutralization to mean we have reached to that point called a neutral point. Why? Because we have water as one of the products. Water is a neutral compound. It has a pH of 7. So what do you expect? That's actually a neutralization reaction. Going forward, you can have hydrochloric acid reacting with a metal carbonate like potassium carbonate. What do you get? Potassium chloride plus carbon dioxide plus water. When an acid reacts with a metal carbonate, the products are salt, carbon dioxide plus water. Don't say carbon dioxide, say carbon dioxide. People will laugh at you. So metal chloride plus water plus carbon dioxide. The same products can be also get obtained when an acid reacts with a metal hydrogen carbonate. Let's give this example. Remember, sodium hydrogen carbonate and potassium hydrogen carbonate are the carbonates existing in solid state. Magnesium hydrogen carbonate and calcium hydrogen carbonate are examples of hydrogen carbonates existing in solution form only. In solution form only. Don't ever say calcium hydrogen carbonate is solid. No. Magnesium hydrogen carbonate and calcium hydrogen carbonate only exist in this world in solution form. That is funny. Just like the way someone can tell you the only metal that exists in liquid state in the whole world, from heaven back to earth, is called mercury. But all other metals are in solid state. But mercury is the only metal that exists in what? In liquid state. Is it? The only liquid that has an nonmetal as its identity is bromine. The only nonmetal that exists in liquid state is bromine.
That's why we have what we call bromine liquid. Yeah. Very good. Very good. But other nonmetals are either in gaseous state or other forms. You see, but the only nonmetal that exists in liquid state is bromine. The only element that can be placed in two different groups is hydrogen. Funny. It has one electron. So what happens here? It can either gain one electron to become stable, you see, or gain 7 electrons. So what is happening here? Chlorine is actually a nonmetal that exists in gaseous state, not like its counterpart, the bromine, that exists in liquid state. Hydrogen gas has one electron in its innermost energy level and its outermost energy level. This element can be able to lose its electron, just like the way the group 1 elements do. This element can as well gain one electron to become stable, just like the way the group 7 elements do. So it can be placed in two different groups, either in group 1 or group 7. Why? Because it can either lose as group 1 elements do, or it can either gain as group 7 elements do. Now, to finish my discussion for today, if you have any question, please be ready to ask that question tomorrow. You'll realize that chlorine has also been able to participate in some other chemical reactions. For example, chlorine being the second element in group 7, as you move down the group, it is the second most reactive element. Its counterpart fluorine is the most reactive. So chlorine has only 3 elements that it can displace from their solutions. What are these? The first one is fluorine, the second is chlorine, the third one is bromine, the fourth one is iodine, and the last one is astatine. That means that chlorine can displace bromine, chlorine can displace iodine, and chlorine can displace astatine. That means that then chlorine can displace only one element, which is what? Fluorine. The rate of reaction among group 7 elements decreases down the group. The rate of reaction among group 7 elements decreases down the group. That means that then fluorine is the most reactive and astatine is the least reactive. So if I have chlorine Cl2 with potassium bromide, you see, potassium the metal, bromine the non-metal. So I want to see if chlorine can displace what? Potassium bromide. How will you displace it? By having the bromine getting displaced from this solution. So I'll have potassium chloride plus bromine. So bromine has been displaced, bromine has been displaced, bromine has been displaced. That tells you clearly that chlorine is the most reactive element when fluorine gets excluded. Bromine is the third most reactive, iodine is the fourth most reactive, and astatine is the fifth most reactive in as far as the group 7 elements are concerned. With this discussion, you realize that chlorine can displace bromine, bromine can get displaced, that is it. Chlorine can displace iodine, and chlorine can displace astatine. That is a very simple summary. That is a very simple summary of how chlorine behaves in as far as its preparation is concerned, in as far as its physical properties are concerned, in as far as its chemical properties are concerned, in as far as its uses are concerned, or its application in our daily lives is concerned, in as far as its compound with HCl is concerned. Now if you move forward and discuss HCl as a compound of chlorine, you'll realize that this compound also has its own physical properties, it has also its own chemical properties, and it has also its own uses. Where are we able to apply this acid called hydrochloric acid? Hydrochloric acid is used in the manufacture of fertilizers. Someone told me one day to actually prove this one. Just look at this. If I have ammonia as a gas, isn't it? And I combine this ammonia with the HCl, what do I get? Ammonium chloride, which is an example of fertilizer. So hydrochloric acid is used in the manufacture of what? Fertilizers. An example is ammonium chloride. Hydrochloric acid is a very important acid in the stomach of human beings. What does it do? This acid helps to provide an acidic environment such that enzymes found in the stomach can act on the food adequately, changing this food from its insoluble form to its soluble form for easy absorption in the small intestine. You'll also realize that these acids will kill the germs found in the food. Just imagine a child picking food from the ground, then taking that food into the mouth. What happens? Does the food have any germs? Yes, it has. So what happens? When the food reaches the stomach, the acid is there to kill any bacteria that may actually be able to have accompanied the food. So the acid kills the germs and as well provides a very acidic environment, isn't it, to better the working of the enzymes found in the stomach. Very, very, very important. Hydrochloric acid also is used to actually neutralize any basic environment in industries. It actually helps to neutralize any basic environment in the industries. This acid will neutralize any excess of any base in any environment within an industry where the manufacturing of different substances is concerned. This acid as well is used to etch designs on metallic structures. You want to have a certain design on any metal used to build your house. The etching of designs on these metals has to actually have this as an acid, which is actually going to be used in as far as that process is concerned. This acid is used to actually be able to descale iron, to remove that reddish brown coat on the surface of iron when it has undergone rusting. We discussed this in form and said that for rusting to occur, there must be air and moisture. Then that means that now the formation of the reddish brown coat, hydrated iron 3 oxide on the surface of iron, can only be removed when this metallic structure gets dipped into hydrochloric acid. The acid washes away the reddish brown coat on the surface of this metal which has actually undergone rusting. Remember, rusting only gets mentioned when we are referring to iron and not any other metal. Unless you want to get laughed at, kindly take note of this. We only refer to rusting or mention rusting in a chemistry lesson or in a room anywhere where chemistry is getting discussed when we are referring to what? Iron. So descaling iron before it is galvanized, or before it is enameled, or before sacrificial protection can take place. You see? So descaling iron. Hydrochloric acid is also used in different experimental activities in the laboratory. For example, at the beginning of my discussion, I said I want to prepare chlorine gas. What do I use? Hydrochloric acid. So, in as far as any experiment is concerned, where having this acid becomes a necessity, then that makes it to become a very important acid in as far as any chemistry lesson or discussion is concerned. I'm tired and I feel I have to take some water. Please kindly, let's make this the end of this lesson. I've tried to give more information as far as this area is concerned. If you have any questions, please kindly be ready to respond to this by asking those questions. Tomorrow we shall have our lesson. May God bless you so much. Have a blessed day. Have a blessed evening. Please make this your best subject, and I love you so much. Mwah. Thank you so much and have a nice evening.